Hello, algebra students. We're going to keep looking at these different patterns that we've been talking about. We're looking at geometric patterns, which means we're doing some multiplying instead of just linear patterns where we're just adding for each of the steps that we go to. So let's take a look here. I think actually I can maximize that. I've got a couple of different figures here, and I want to be able to find a way to state what the area is for each of them. So let me move that up just a bit. For this one, the first one, you can see it's just one big square. For B, it's a big square, but it's taking out a 1 by 1 small square. And in figure C, I've got two of the big squares, plus it's adding one of those 1 by 1 squares. So in the first picture, for the area of A, if I just say that my side length is 4, this is a 4 by 4 square. 4 by 4 would give me 16, right? That was really just 4 times 4. For the area of B, it's still saying that each side length is 4. So this is 4. This is 4, and I know that some of you are jumping right to saying, well, it's 15 because I'm taking away 1, and that's true, but it's really that 4 by 4, instead of 4 times 4, I'm going to say 4 squared, and it's going to subtract 1. Then yes, that is 15. For the area of C, that's really saying I've got, this was a 4 by 4, and this is a 4 by 4, so I've got 2 of those 4 by 4 squares. But I'm now adding on 1 extra. And again, this one we can certainly figure out what that is. We know that 4 squared is 16. 16 times 2 would be 32, plus 1 would be 33. Now, when I had just a side length, I could easily figure out what that actual number was going to be. However, when I now change this, and instead of having a number, I have a variable. So for instance, if my side lengths are x, this is x, and this is x, well, the area of the square's length times width, so it would be x times x, which would be x squared. Well, in B, it's also x by x, but I'm going to take away that 1, so it would be x squared minus 1. Look at how similar it looks to the one right above it. In figure C, again, I would have an x by x, and then another x by x. So I've got 2 of those x squared areas, and I'm adding 1 more on. When my side lengths now change to, instead of just x, we're going to say this is a 4x, a 4x. It'd be really tempting to say 4x squared, but it's not. Remember, this is really the whole thing squared. So 4x times 4x, which would be 16x squared. Or we could have left it like I had it with the parentheses, 4x in parentheses squared. For B, again, if this is a 4x and this is a 4x, then not worrying about that 1 that we're taking out, I would have exactly the same thing that I did from the area of A. So it would be 16x squared, but I'm going to take away that 1 by 1 square. And in figure C, this is where it gets a little bit more messy, right? I have an x by x, and I have another x by x, so I have 2 of those 4x things that are both squared, and I'm adding 1 on. Now I'm going to have some extra space over here. We know that that stuff in the parentheses, that 4x quantity squared, is really 16x squared. Times 2 is going to give me 32x squared plus that 1. Now for this last one, I have to erase all my mess up here. Each time they're saying that a side length is really x plus 3. So where it was easy for me on this one to say, oh, I know that 4x quantity squared is just 16x squared. We haven't really learned how to do x plus 3 times x plus 3 yet. We will, we just don't know it yet. So this is x plus 3, and this is x plus 3. I would say that this would be x plus 3, the whole thing is squared. By now, hopefully you're seeing the pattern now for area of B. It's just going to be that same thing, minus 1, right? So I would have x plus 3, quantity squared. Quantity just means the whole thing is in parentheses. And I'm going to take away that 1 extra square. And for C, I would have 2 of those x plus 3 squares. And I'm going to add 1 on. So I would have 2, and then in parentheses, x plus 3 squared. So I've got 2 of those big squares plus the 1 extra little square. Okay, so this is just how we can represent those different areas, thinking about what we know already about exponents, what we know about area, trying to pull some stuff together here. In this activity, I've got these different shapes, and they're made up of these little squares. We do a lot of these square kind of things. So in step 1, the shape that I have here has this 1 square in the middle and 1, 2, 3, 4 on the outsides, right? Notice that all 3 of these steps have those 4 on the corners. Step 2 is this in here, and I know I just colored over the lines, but that's a 2 by 2 square. And in step 3, this is, I guess I won't color it in, I'll just outline it. That's a 3 by 3 square, right? So I know it's asking what I would see in step 5 and what I would see in step 18. Not asking how many there would be. I need a little bit of space for that. But in step 5, it would have a 5 by 5 square plus the 4 in the corners, right? For step 18, it would be really big. I wouldn't want to draw that out, but it would be an 18 by 18 square. And then I would have the 4 on the corners, right? So that'd be 18 by 18 plus the 4 corners. So sketch or describe what's happening in each of these. That's what we just did. We just described it. I didn't actually sketch it out. How many small squares are in each of the steps? And let's figure out how we know that. So we know that that middle part is the step number, whatever step I'm on, squared, because it's making an actual square there, plus the extra 4. Now it's always adding 4. That's a constant that's getting added on every single one of those. So, I mean, you could certainly figure out in step 1, I've got 5 little squares. In step 2, let me erase my coloring here. I have 2 by 2, which is 4, plus those 4 would be 8. So it might be tempting just looking at that and say, oh, it's just adding 3 every time, except it's not. In step 3, I have a 3 by 3, so this part is 9, plus those 4 would be 13. So there is definitely a pattern if we would write out more of those, but instead of trying to look at it that way, I want you to be seeing that for each of those, we're taking the step number. So any step number that I have gets squared and we add on 4. So when I asked how many small squares we would have, in the 5th step, this one, I would have 5 by 5, which would be 25, plus 4, which would give me 29 small squares. In the 18th step, 18 times 18 would be 324, plus the 4 on the corners would give me 328 of those little squares that I would not want to draw all out, right? But that's how we can find that pattern. By the way, I know it doesn't actually ask for this, but here's how you would write that pattern. You would take whatever step number you had, we use n for whichever one you want to pick, and it gets squared. That tells us that square in the middle, and then every single time we're going to just add on 4 more, 1 on each corner. And Right here is where it just asked that. So we just did that one, sorry. It says be prepared to explain how you get this, but again, we just talked about that, right? We said whatever step number you want, we're going to square that. So n is the step number. We're going to square that, and then we add the 4 on each corner. And that's going to give me my total number of squares. Okay? So you can certainly make a table if that helps you, but I think seeing this pattern and looking at 1 squared and 2 squared and 3 squared kind of helps with that one, just visually seeing that pattern. Number 3 says, sketch the first 3 steps of a pattern that could be represented by the equation of y equals n squared minus 1. Okay, so if we are looking at n squared minus 1, remember n squared would just mean that I would have whatever step number I'm on, it's going to be a square. So it'll be like the first step would be a 1 by 1 square. But it says that I'm going to take away that square. So in the first step, I'm actually not going to have anything. In the second step, let me just do this. I would have 2 squared, which would be 4. But it's taking away 1. I'm just going to take away the top right corner on all of these. So that's what that one would look like. The next one would be, for the third one, would be a 3 by 3. But I'm going to take away 1. I'll take away the top corner. I know, not very squarish. I'm very sorry. But that's what our pattern would look like. So each time, the length and the width are increasing by 1 for each step. And we're going to just take away 1. I just chose to take away that top right corner, but you could take away any of them that you wanted to. In the first one, remember, there's 0 squares because 1 square is 1, but then I have to take away that 1. So there's nothing left. All right, so now that we've done those patterns, it says for that original step pattern in the statement, write an equation to represent the relationship between the step number and the perimeter. Now they're going back to this original one. So let's talk about the perimeter now. The perimeter on these blue squares that I've drawn, now I know for sure that, there's a different color I guess, the perimeter of this is 4. And the perimeter of this is 4, and this is 4, and this is 4. So every single one of these I'm adding 16, just with those outside squares. In step 1, this perimeter was also 4. In step 2, I have a 4 and a 4 and a 4 and a 4. Sorry for the bell, there's going to be another one in a couple of minutes. This perimeter was 2 and 2 and 2 and 2, which is 8. Okay, so I had 8 here plus the 16 around the outside. This was 4 from the middle plus 16 around the outside. Let's see what happens in step 3. I would have 3 and 3 and 3 and 3, which is 12, plus the 4 squares around the outside, which was that 16. Now I know I didn't add up the total here, but I want you to see that every single time, because of the 4 squares, that's always there. That's where that 16 is coming from. Look at the perimeter of that inside part, right? Step 1 had a perimeter of 4 for that inside part. Step 2 had a perimeter of 8. Step 3 has a perimeter of 12. I want you to see that what's really happening there, because it's a square, because I've got 4 sides that are all exactly the same. If this was 3 right here, it's going to be 3 times 4 to get that whole perimeter. This was 2 right here, it's going to be 2 times 4 to get that whole perimeter. And the first one is 1 times 4 to get that whole perimeter. So let me step back to our problem that we're on right here. So the step number would be we had 4 times the step number, because whatever the step number was, that's how long each side was. And we had 4 sides of that square. Plus, because of those 4 extra squares around there, every single time we would add that 16. So that's what my perimeter would look like. We're just working on building these equations, finding the patterns so that we can represent them as an equation. Okay, so now this says for the step pattern that you created in part 3 of the activity, part 3 was the one with the square minus 1. That's this one. Let's find out what the perimeter is there. All right, so let's take a look at this. Step 1 actually had a perimeter of 0 because there wasn't anything there. Step 2, now remember, I don't care about the inside part. I'm just counting the outside part. So I've got 2, 4, 5, 6, 7, 8. For the 3 by 3, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I'm hoping we don't have to keep drawing this out to find it, right? The perimeter here is just whatever the step number was times 4. I know that I took squares out. I know that it decreased the area, but in terms of perimeter, having this segment versus this segment wouldn't really matter. Having this segment versus this segment doesn't really matter. Either way, I'm getting the same number of segments all the way around the outside of it. I just took this and kind of collapsed this part down and made it into this part for my perimeter. So every single time, my perimeter is just 4 times the step number. So the perimeter is 4 times the step number. Now, are these linear? Well, yeah, I mean, these look like slope-intercept form, right? Instead of p's and n's, what if I had y equals 4x plus 16, or just, sorry again, y equals 4x. Those look like slope-intercept form, so these are linear. They have a constant rate of change. They're always increasing by the same amount every single time. Now, here's a new pattern to look at. It says sketch the next step in the pattern. And I don't have a whole lot of space on here, but in your book you've got more, or on your paper you've got some more space for this. Can we figure out what the pattern is right now? So the step number, I want you to notice the step number is matching up with the base of these rectangles. Step 1 has 1, step 2 has 2, step 3 has 3, right? Let's look at the height of these rectangles maybe. Step 1 is 3 tall. Step 2 is 4 tall. Step 3 is 5 tall, right? Here's 3, here's 4, here's 5. So I can tell what the pattern is. It's increasing by 1 for the width because of the step number increasing. And it's increasing 1 in the height because that's just what our pattern is doing, right? So the next step in the pattern should be 4 across the bottom, and it would be 6 tall, right? Instead of sketching it, I'm just going to say that it's going to be a 4 by 6 rectangle. Karen says that the pattern is growing linearly because as the step number goes up by 1, the number of rows and the number of columns also increases by 1. Do you agree? So I would say that Karen is right that they're both growing, but because it's growing in 2 different dimensions, that means it's not going to be linear. Take a look at how many squares I have. If it's linear, I should have a constant rate of change. In step 1, I had 3 squares. In step 2, I've got a 2 by 4 rectangle, which is 8 squares. That increased by 5. But in step 3, I have a 3 by 5 rectangle, which is 15. That is not a constant rate of change. So it's not linear. And again, it's because it's not just growing in 1 dimension. It's not just adding on to the length or just adding on to the height. It's changing in both of them. And when we find the area or the number of squares, we end up multiplying those two things. So increasing in both of those dimensions makes it not linear. So do you agree? Nope, not a constant rate of change. Okay, here's my abbreviation. Not just because Crocs are the best shoes ever, because I love Crocs, but it's a constant rate of change. That's my abbreviation for constant rate of change. To represent the number of squares after n steps, any number of steps, Diego and Jada both wrote different equations. So Diego wrote this, and by the way, we really haven't talked about function notation yet, but function notation is this. This is just taking the place of a y. So you could just imagine that that's just y equals n times n plus 2. And this is just y equals n squared plus 2n. Are either of them correct? So when we're looking at the pattern here, in Diego's, I'm seeing this in terms of length times width, or base times height of my rectangles. The n, remember, was the step number. Step number is 1, it's 1 across there. And the height is really 2 more than what I started with. So it's a 1 by 3. So that's the height part of it. This is like the base and this is the height. So in step 2, step is 2, that's the n, and then n plus 2 is 4. That one works. And then for step 3, step number is 3, so that's my n. The n plus 2, oh yeah, that's 5. That does work out with the 3 and the 5. So what Diego has there is correct. We're looking at base times height. We're looking at finding the area of the rectangles. Now, for Jada's, let's look at that. And I have a feeling that maybe not everyone sees it this way right away, but I want to help you find this pattern. In this one, for Jada, Jada is saying that I'm going to take the step number and square it. Okay, so we've done that a couple of times already. So here's my step 1, and it's squared. And in this one, step 2, squared. Step 3, 3 by 3, and it's squared, right? Now look at the part that I didn't outline. In each case, there's 2 rows, and they match the step numbers, obviously, because that's what the width is going to be. But that's saying that I'm going to have 2 of the step numbers, right? So step 1, I'd have 1, 2. Yep, that's 2 times n. Step 2, I would have 2 times 2. Oh yeah, 1, 2, 3, 4. That works. Step 3, I would have 2 times 3. 1, 2, 3, 4, 5, 6. Yeah, that works. So actually, Diego and Jada both have equations that work, right? So we can see how that's happening there. And I want to be able to take a look at that algebraically. I want to be able to see why that works. So if I take Diego's equation, or just his expression, I'm going to take a look at n times n plus 2. Think about our distribution. N times n, that would be n squared, plus n times 2 would be 2n, which is exactly the same thing that Jada wrote. So it's just 2 different expressions that mean exactly the same thing. Okay, here are all the answers that we just went through. All right, for this lesson synthesis now, this is kind of putting everything all together. So how do you know if the relationship between 2 quantities represents a quadratic function? And again, we haven't really even used that word very much yet. But a quadratic function is where we've got something being squared. Right, in almost all of our patterns here today, we were looking at taking the step number and squaring it. So we would get like an x squared or an n squared. So a quadratic function, a lot of times we do look at this in terms of area because we're multiplying a length times a width. But the clues that I'm going to look for is I'm going to look for a squared variable. we were almost always using n for our step number, but really that's in terms of looking at just the equation, we are looking for some variable that's getting squared. That's how we get a quadratic. That's how we get this pattern that we're looking at. If we're looking at an actual pattern and trying to find it, you should be seeing if there's something that has like an actual square, like 2 by 2 square, or 3 by 3 square, or 4 by 4 square, right? So we're looking for something getting squared. This one, the second question says, what does it mean when we say that two expressions define the same function? That's just like the Diego and Jada problem that we just looked at. They both wrote expressions that worked. They just looked a little bit different until we did some algebraic manipulation. When we move things around, when we do some of the algebra stuff that we know, like we can distribute, we know how to do that. We can get two expressions that might start by looking different, but they end up giving us the same information. And that's what this one is getting at here at the bottom. And again, I know this isn't on your paper for what you'd be looking at, these three questions. It says, can we say that x times x plus 5 and x squared plus 5x define the same function? How can you show if they do or they don't? This is a distribution, right? X times x plus 5, if I distribute, I'll have x squared. X times 5 is 5x, which is exactly that same thing. So that's just the algebra part of it. We know how to take care of that stuff. All right. This cool down, now we're looking at this new pattern of squares. It says write an equation to represent the relationship between the number, step number, and the number of squares in the pattern. Briefly describe how each part of the equation relates to the pattern. So we're going to talk our way through this. But again, remember, we're looking at quadratic things. We're looking at squaring something. You should be looking for squares in our pattern. And I have squares. I'm going to go with this right here is my step number squared. And then I'm adding on this one extra square. I'll get back to that one in a second because I think it gets easier as we see more of it. Here is our step number squared. And then I've got 2, which happens to match our step number. And then I've got 3 squared for a step number plus 3 more that matches our step number, right? So that first one that I outlined in each one of those would be my step number getting squared. And then I can add on the extra squares that are getting added, just match the step number. So whatever the step number was, whether it was 1 or 2 or 3, that's how many extras are getting added on. So question 2 says, is the relationship between the step number and the number of squares a quadratic function? Okay, now we've used this word quadratic a couple of times. I know it's still not real familiar, but quadratic means that I've got something squared. Yes, I have something squared. That n squared, that step number squared, that's my quadratic. Either from the equation, seeing that 2 right there, or seeing the square that I can draw in my pattern. That's where I'm getting my quadratic from. So yes, it is a quadratic function. All right, so this is in your papers now. This is the summary. This is just going back through everything that we did here. So it says sometimes a quadratic relationship can be expressed without using a squared term. So let's take a look at this. And I said quadratics have things that are squared, right? So that's what we usually look for, but there are ways to do it without that. And we did look at some of those problems also. So for this, I can see that I have the length and the width are each getting increased by 1 each time. And let me do my cool little outliney thing. Step 1, here is my first step, and then there's some added. Step 2, 2 by 2 square, and a 3 by 3 square, right? So you can see that pattern that way. Or we can also be looking at it in terms of just the length and the width for the area. The step number is 1, and this is 1 more than that. This is 2, and this is 1 more than that. So this is n and then n plus 1. This was n for step number 1 and n plus 1. This is 3, but this is 1 more than that. And then n plus 1. So I could write that area as n times n plus 1. But again, we know, we're good at algebra, we can do this stuff. I know that that could be kind of cleaned up and simplified. It's equivalent to this, which then brings in that n squared. That's where we get our quadratic from, okay? So you could visually show it. Yeah, I did that outline thing, but here they've got it kind of broken down. Here is step 1 is 1 squared plus the extra n. And then here's a 2 by 2, and here's a 3 by 3. And the extra that's added on there every single time is just whatever step number we're on. That's what's getting added. Okay, so today, would you please make sure that you check Schoology, see what's in there for an assignment, besides just going through these papers and filling things in with me. If you need any help, let your teacher know.